Hello again, welcome back. Today we're in section 2.3 and we're going to be talking about graphical misrepresentations of data. Okay, so the most common graphical misrepresentations of data involve the scale of the graph, an inconsistent scale, or a misplaced origin. All of these things can trick the eye so that the author, whether intentionally or unintentionally, misleads the reader. Let's look at this graph. A home security company has the slogan, "When you leave for vacation, burglars leave for work." According to the FBI, roughly 18% of home burglaries in 2009 occurred during July and August. The advertisement contains the graph below. What's wrong with this graphic? Well, if you look closely at it, they have the months of July and August broken out, and they are displaying the total percentage of burglaries that occur in both July and August, but for the other 10 months they have an average per month. So if we averaged this, if we divided by 2, because we're talking about 2 months here, we'd have 9%, which is not that drastic of an increase over the other months. Here is the same data presented as a bar graph per month, and you can see that there is an increase in July and August, but maybe not the drastic increase that the company wanted you to see. And here's another example. In 2005, Terry Schiavo was the center of a right-to-die battle. A CNN USA Today Gallup poll conducted in March 2005 asked respondents, "As you may know, on Friday the feeding tube keeping Terry Schiavo alive was removed. Based on what you have heard or read about the case, do you think that the feeding tube should or should not have been removed?" The results were presented in the following graphic, and it shows that Democrats agreed much more strongly than either Republicans or Independents. Only the problem is that if you look closely at this graph, the vertical axis does not start at 0. Let's look at the same graph but zoomed out so that we can see the entire vertical axis. So when we zoom out on the graph so that the vertical axis starts at 0, we can see that the bar for Democrats is taller than the other two bars, but it's not as drastically taller as the original graph would have had us believe. I want you to notice how your eye picks up on not so much the height of the bar, but the difference in height between the bars. And unless you were trained to look for it, you might not even notice that this vertical axis starts at 53. See, you see this little short bar here and you just think that's not very much, but really it's over half of both Republicans and Independents who agreed with the ruling. Now let's look at this example. The time series graph in Figure 23 depicts average SAT math scores for college-bound seniors for the years 1991 to 2009. Why might this graph be considered misrepresentative? Well, again, it's a similar problem to the one we saw in the previous example. The vertical scale starts at 495, so this bar appears very short, and it looks like these bars are much taller. I would guess 4 or 5 times taller. So you get the idea that there's been a large increase in scores. But if we look at the same graph zoomed out so that the vertical axis starts at 200 instead of 495, you can see that the scores do rise and fall just a little bit, but not as drastically as they would have had us believe before. Now here's the same data presented as a time series graph instead of as a bar graph, and you can see that they put a little break in the axis to draw the reader's attention to the fact that we are zoomed in on the vertical axis. So there's nothing wrong with zooming in to make a difference in height clear, but you should always make sure that the reader realizes what you've done. Also, be aware of pictographs where perceptions of area and volume can mislead the eye. In this graph, we really don't know if the roll itself is part of the graph or do the bars start at the top of the roll. It's just not clear. And in this graph, we see that soccer participation in 1991 appears much smaller than participation in 2007, but with a 3D object, if you double the width and double the height, the eye perceives a difference of 4 times, not just 2 times. So it might be better to do something like this, where each ball symbol represents a certain number of participants. As another example, I think we've all gotten used to 3D graphs since we all have such easy access to Excel and PowerPoint. Only because we're looking at the bars at an angle, it makes it difficult to tell the difference in height between the bars. If you really want your reader to be able to perceive the difference in height, instead of using a 3D graph, just use a regular two-dimensional bar graph. That makes it easier for the eye to tell the difference in height. So these are just some of the things to be on the lookout for as you're reading graphs and also as you're preparing graphs for other people to use. You never want to mislead the reader. The purpose of a graph is always to make the data easier to understand, never to make it more obscure.